and today I'll be talking about the inverse kinematics and collision avoidance method we are working on together with my colleague Pragna. Um, Next slide, please. So I would first like to give you a view on what we're trying to achieve and why we are trying to achieve that. In RAIN project, our group is particularly interested in glove boxes, and these are contained volumes that help operators to manipulate contaminated objects. And the inside of a glove box is usually cluttered. It's unstructured and can also be considered as dynamic. While working with a robot inside a glove box, we have to make sure that there won't be any unwanted collisions, either with the environment or with the walls of the glove box, or even between two robot arms that we're planning to use. Next slide, please. Here we see our glove box mock-up system, even though it is not really cluttered compared to the reality, it is still giving us an idea on what we should expect when we deploy these robots to real glove boxes. And next slide, please. I think that's fine, yeah. So our goal is to utilize the available redundancy in our system. And using the redundancy, we would like to achieve inverse kinematic solutions, which are both avoiding collisions with the objects in the workspace, and we're looking for solutions which are away from singularities. We identified these two as important metrics for our work. As I said, collision avoidance is related to the safety of our telemanipulated system, and also the safety of the contaminated objects and the glove box. Singularity, on the other hand, is something that will help operators to work for longer hours and with an easier interface, so that they won't need to deal with releasing the robot from a singular configuration. And next slide, please. So how we do it, we are proposing an inverse kinematics algorithm. We call it multi-criteria IK. In our inverse kinematics solution, we utilize two different objectives. As I stated before, we are interested in, we're going to make changes in our inverse kinematics by considering the collisions, and on top of that, or together with that, we're going to make some changes in the inverse kinematic solution, considering the manipulability, or which is basically a way of measuring the singularity of the robot. Let me stress this out one more time. We are interested in redundant manipulators because that redundancy is key to our inverse kinematics algorithm, and our approach tackles the inverse kinematics problem at the velocity level. So we will be utilizing the kinematic Jacobian of the robot. And next slide, please. So basically, this is a broad view of what we are doing. We are solving the inverse kinematics problem at the velocity level. So for a given end effector velocity, we calculate the joint velocities, and then we integrate them to obtain the joint positions. Here, what we see is that the first part of the first equation, which is J times x dot, that's kind of very conventional in robotics. On top of that, since we have the redundant manipulator, we are utilizing the null space of it. By null space, what I mean is that there are certain joint velocities which will show no effect at the end effector. And by selecting those null space velocities or joint velocities, we can achieve some of the goals we identified at the beginning. For our case, it is the collision avoidance and singularity avoidance. So the rest of this talk will basically focus on how to select that Z value. Next slide, please. So Z can be an arbitrary value. It's up to us. As I said, Z has no effect on the end effector velocities that we will observe. There are methods for selecting Z. The most conventional one is defining a potential function and equating Z to the gradient of it. So basically, we're trying to maximize a potential function. And in our case, we define two separate potential functions. One potential function for collision avoidance and the another one for singularity avoidance. Next slide, please. So basically, the first one, the collision avoidance, which will be talked in more detail by my colleague in a minute. The second one is the manipulability of the robot, and we selected the well-known manipulability measure of robots. We're checking the determinant of the Jacobian, and we're trying to identify where it fails, where it loses a rank. Next slide, please. So, as I said, we have two objectives here, one for collision, one for singularity. However, we want to achieve this solution, achieve an inverse kinematic solution, which can handle those two at the same time. So what we do is that we combine those two potential functions using weighted sum and obtain one single potential function. And we continue our work with this combined overall potential function. Sorry? Okay. So just reminding you what multi-criteria IK is doing. We are solving the inverse kinematics for redundant manipulators. And since they are redundant, we are interested in utilizing the redundant joints so that we can achieve better solutions, better in quotation marks, of course. So how do we do that? We define our potential functions. We combine our potential functions into one big potential function, which consists of manipulability and singularity avoidance. So my colleague, I think from now on, will be talking about how we achieve collision avoidance in this context.
Yes. Sorry, I was not able to unmute myself. So, can you still see the slides?
Yes, we can.
Okay. So, we are now talking about how we can model the collision. So,
before you continue, Pragna, could you please do presentation view?
Oh, did it stop?
Yeah. All right.
Yes. So why we need to model the collision rather than computing it while we do the IK? Because it is fast if we model it and just get the collision values. And we present a very simplified and straightforward method. We train a neural network to mimic the collision function for rapid approximation of the cost of collision. And we just input any given combination or any given position of the joints and the position of the centroid, and we will get the collision. So that is the idea here. Now, how we conceive the cost of collision. When we have an arm, we calculate the distance between the midpoints of the links and the centroid, and we take an exponential of summation of those distances, and then we take the exponential of those distances and make a sum, and that is our cost of collision. So in this picture, it is depicted that we have a centroid of the obstacle, and we measure the distance, which are d's, and then we take the exponential of it and make a sum. So what we are trying to do is we first get the inverse kinematics, the forward kinematics of the links, to get the midpoints. And then we also get the positions of the centroids. So that's how we can get the exponential of that. And then we make a sum of it. So here in one sample of training data, we have the input joint positions, we have the centroid positions. Given these two, we create the ground truth by the previous method. And now we have a sample. So we have the ground truth for each set of configurations and the centroids. So we train the neural network to mimic this function, which is the cost of collision. So how do we train it? We train using a fully connected layers. We have 3 fully connected layers, and we have rectified linear units between them. Because since this is a nonlinear function, the rectified linear units add the non-linearity to the model. And then we expect the cost as an output from the model as a single floating point. Then we do stochastic gradient descent with a learning rate of 0.0005. And also we use random dropouts at the time of training. And we have used 50% of the neurons to be dropped out to prevent the overfitting. So this is the result of the training. We had 1 lakh training samples. Among them, 80% were randomly selected for training and the rest are selected for validation. And we have trained it for 500,000 iterations. So here it shows the training loss and the validation loss, and the mean and the standard deviation of 2 different validation sets. So you can see the mean square error between the expected cost, which is the ground truth, and the estimated cost from the neural network, and also is the mean. And we also plot the standard deviation of the error. So it's to the order of 10 to the power minus 5, and they're quite close to each other on both the sets. So in one set we get 5.89, in another set we get 6.034 to the power of 10 to the power minus 5. So the standard deviation of the error between the ground truth and the estimated cost in the validation is pretty low. So that's how the training is done. Now, once the training is done, we have this least square IK solution. This is the baseline solution, that there is no obstacle, nothing is there. So then the robot solves the IK for its starting position to reach the goal position. But when we have an obstacle like this here, what do? We use the neural network to give us a estimated collision cost at each step of the IK, and we will augment that to the IK optimization. So we choose a random obstacle, dynamic obstacle, but it's not so random that it is outside the glove box area. So it's this line in the graph, 3D graph, shows the trajectory of the obstacle, where the obstacle is moving. So what we do now, we have this IK optimization. So this Z is the weighted gradient of the cost of collision with respect to the joint angles. So at each step of the IK, we get the joint angles, and then we do the gradient of the cost of collision with that joint angles, and then we get this Z, and then we do this optimization using this equation, so to get the next step of the IK. So here we get the result of the IK. On the IK least square is that baseline solution where there is no obstacle, nothing is there. And IK with collision avoidance is the solution where we have the Z, which is the gradient of the cost of collision with respect to the input angles. So this Z actually drives the IK or away from the obstacle. So you can see there are changes in the movement in Q3 is the third joint angle, and then we observe changes in Q1 little bit. The most visible change is in Q3. Here, this graph shows the cost of collision we obtain from the neural network for each step of IK. At each step, we get the joint angle. And the obstacle centroid also we get from the trajectory. So we input that into the neural network and we get the cost of collision. And again, we also calculate the cost of collision analytically using the function, just to compare how we are getting the cost of collision. So you can see the graphs are almost the same with very similar values, and the nature is also similar. And sorry, one more thing. And also you see with the progression of IK, the cost of collision is gradually decreasing. So the IK chooses those input, those joint angles for which the cost of collision decreases at every step. So we are minimizing the distance between, sorry, we are maximizing the distance between the centroids and the joints through minimizing the cost of collision. Now here you can see the distance of the joints in the collision avoiding trajectory and also in the least square trajectory. So in the least square trajectory, and also the distance between the joints in the collision avoidance trajectory, they start at similar point, but for joint 3, joint 2, it moves a little bit ahead from the beginning, then it crosses and moves closer to the object at the end. So this crossing point is that moment where the obstacle was supposed to collide with the joint, and it sufficiently moves away from the centroid from the beginning of the IK, from the beginning of the IK. While in the least square trajectory, the distance is closer to the centroid. So this result shows that the Z, which is the gradient of the cost of collision, is actually driving the IK away from the centroid. That's why the distance from the beginning is more than the previous distance. It's similar also in joint 2 and 4. This is the distance of the midpoints. Here also we see a similar pattern. So this is the way we can see that the IK is actually choosing those joint positions away from the obstacle. Thank you, everyone. So this is it. Questions?
Thank you, Pragna. Does anyone have any question for Ozan or Pragna, or we can go to
Yes, I have one question.
Yes.
So have you compared your algorithms with relaxed IK?
Yes, we have qualitatively compared it. See, relaxed IK is a very complex optimization. First of all, they are using a lot of optimization, but here we propose a very simple framework just for collision avoidance. This work deals with that. And moreover, the collision avoidance here is we present a different network layer than which is used in relaxed IK. So the network in both the works are not similar. It's different. And but in terms of what should I say, quantitative analysis in terms of performance, the collision avoidance model works 4 times faster than manual computation. But we are yet to compare quantitative matrices with relaxed IK, but we are in the process of doing it. But qualitatively, I can say that it's a single framework through which one can just input the joint positions and get the collision avoided. That's all.
So for in so in terms of the computational speed, so how fast is your algorithm?
How fast is our algorithm means?
Yes. So like to calculate the joint angles commands. So in each second, how fast can you calculate?
So you want to know that how fast is this?
Yes, because I know relaxed IK.
taking.
Yeah, because I know relaxed IK it's very fast now. So for example, every second that you can calculate the 3,000 times of the solution.
We haven't quantified how fast it is solving, but we can have a guess that it won't take long, because we are doing a matrix inversion and some matrix multiplication and addition, and that's it.
Okay.
So on the other hand, some other approaches, they rely on optimization problems which needs to iterate it more than a few steps. So it should be relatively faster.
Yes.
Okay.
Okay, thank you. Hanlin, do you want to set your slide?
Yes.
If anyone else have any question, we can go back in the discussion at the end.
Okay. Can you see my screen?
Yes.
Okay. So my presentation topic is asynchronous parallel learning with guidance laws for collision avoidance in unknown environments. The target robot platform is a mobile robot. However, we can also implement these algorithms into manipulators. So first of all, I will introduce the basic algorithms, deterministic policy gradient algorithms, which we call the DDPG. And I will show how we integrated it with human demonstration data last year. And I will also show how we improved the last year's work this year, and we integrated the asynchronous DDPG with guidance laws. First of all, this is the pseudocode of the DDPG algorithms. The left side shows each step of DDPG. The right side shows the overview of the DDPG. So DDPG is one of the deep reinforcement learning algorithms that generates continuous outputs for the control command. And it's different with the DQN, which was used for the AlphaGo to help the computers to beat the human in the Go game. So in the DQN, it will generate the discrete control command, like playing the Go game. It can only go forward and so forward or left, and it will generate the discrete control command. But for the control for the mobile robot or for the manipulators, we want it to generate a continuous command. So that's why we choose the DPG as the basic algorithm. So for deep reinforcement learning, it has a nature of trial and errors. And on in the right side, it shows the overview of the DDPG. So for each DDPG algorithm, it needs 4 networks. One is the critical network, one is the actor network, and also their corresponding targets critical network and also target actor networks. So what does the critical network and actor networks do? So critical network, it will judge whether it's actor network and also its current state, whether it's a good combination or not. It will say, okay, the robot you are doing a right command, and the actor you are generating a wrong command. And so we put the robots into a simulation environment. We call it environment. We put the robot into the environment, and then we train this robot. So in the environment, we will read the state of the robots. So for the mobile robot, we will read its laser data to read its relative position between itself and the target position, and also its current state. And its current speed. So we evaluate that state, then we calculate the actions using the actor network, and then we calculate its TD area to update the value function. So the critical network will be like a teacher to judge the actor network to see if it's good or not, and then we also have a reward function to evaluate if the robot is going forward to the target or is having a collision. For example, if the robot is going to, if it moves forward, moves toward to the target, then we will give it a positive reward. Then if it has a collision, we will give it a negative reward. So on the left side, it has the pseudocode of the DDPG algorithm. So in the beginning, we initialize these four networks, and then we initialize a replay buffer, and then we go to the iteration loops. And then in the beginning, we initialize a random process for action exploration, because in the beginning, the robots, it knows nothing, and it needs to explore some random action to try which action is better. And then we select action based on this current actor random policy, and then so in each time step we will execute its action command, and also we observe how much reward it can receive, and then we observe a new state. We put all of these transition data into the replay buffer, and then we will sample a mini batch transitions from this experienced replay buffer. And then we use these two equations to update the actor network and also the critical network. And also we correspondingly we update their target networks. And then this is the neural networks we used for the actor network and also critical network. And for this one, the first one is the actor network. We use its current state, includes these laser data, relative position, and also its speed command. And then in the middle are three fully connected layer. Includes three the resolution ReLU activation function. and then it will generate linear velocity and angular velocity, and then we merge it as the external network's outputs. We call it action. And we then for the critical network, it will evaluate the current state and also the output of the external networks, and using another fully connected layer to output the Q value function. And last year we integrated the DDPG with human demonstration data, like what I said in this page. In the beginning, for the original DDPG, we are using random action actor networks to have either to explore random data in the beginning. But in the last year's work, we use human data. So we make the operator to teleoperate mobile robot to move from the start point to the target, represented by this red ball, and this black square is the mobile robot, and this blue laser data it shows the range of the laser, and this robot, it has no information of the whole map. It can only sense the obstacles that is in the range of this laser data. That's why we also call it mapless collision avoidance algorithms, because it doesn't need to know the whole map's information. So we make the operator to teleoperate this mobile robot to the target. Then after 30 minutes teleoperation, and then we install all of the human data into this experience buffer, and also we make the robot to explore by itself. We merge these two experience data, and then we sample it using prioritized experience replay algorithm to train the DDPG networks. And then this is how we integrated them. We integrated the DDPG with the human data using prioritized experience replay. The capital PI is the sampling possibility of each transition data, and the small PI is the transition priority. If it's human data, then we will give it a higher sampling priority, and the omega PI, it is the neural networks are updating weights. So if it's a human data, we will sample it more frequently, and then we update the corresponding to networks, which is the active network and also the critical network. In the beginning, we trained the robots in the simulated environments. So on the left side is the DDPG with human data. And then we found if we use the human data, the robots only need to play 1 hour and 50 minutes. Then in 20 random missions, it achieves no collision. But on the right side, if we use the original DDPG, even after 3 hours and 45 minutes, it still have a collision. So we can say the human data it accelerates the training process, and then we compare the Q values and the reward. We found that using human data, the Q values and reward it increase much faster than the original DDPG. So like the reward, it use around 20% of the steps required by the original DDPG. For example, it only use 10,000 steps, and but to be above 0 for the reward. But using the original DDPG, it needs 50,000 steps. And then we tested it. So we integrated the trained weights into the real robot directly. We found that using the original DDPG, it couldn't even avoid the first obstacle. And here I put the 4 rubbish bins in the corridor of circular street building, and we found that using original DTP, it couldn't even avoid the first obstacles, but using our proposed algorithms is more robust than DTPG, and it just avoid these 4 obstacles. We can see this part. So I tested it in different environments, and it's quite robust. Like this one, and this one, it just avoid these 4 obstacles, and it went to the end of this corridor. And then this year we instead of using humans data, because for recording humans data we still need sometimes for example in this work I used 30 minutes humans data and plus the training the training time, then I used around 2 hours and 15 minutes for this training. And this year we improved it using some traditional algorithms like some path following algorithms and also collision avoidance algorithms. So we have some simple algorithms that can teach the robots in the early stage, like the nonlinear guidance law for the path following algorithms. We can make the robots to move from start point to the destination without the training, because we have this simple algorithms. We can play it directly. So I put it into the simulated environment to make it to collect the data from traditional algorithm directly. So for the nonlinear guidance law, the robot's position is represented by the symbol O, and either need to move from start point to the destination. So it will plot a circle, and for the intersection point N, it will always move to the N, so it can move forward to the destination. And we also have some simple collision avoidance algorithms like this one. So if it meets with obstacle, it will just turn. And this is okay for the simple collision avoidance scenario. So it's like a human. So when we were a child, then we started to learn from very simple tasks. So like this one, I make it to learn from simple collision avoidance scenario to just avoid one single obstacles. And then we integrated it into a more complex scenario. So instead of using one robot to learn, so I used multiple CPUs to utilize multiple threads to trigger multiple robots to learn simultaneously. So in the left two threads, I used the nonlinear guidance law and the collision avoidance algorithm. These two traditional algorithms to manipulate the robots to go to the environment to collect their experienced data. And on the right side, I have several threads to trigger the robots to learn by themselves. Then I merge their experienced data and then use sampling strategy to update the corresponding critical network and active network, which is a separate training thread. So we have the action, we have the extra thread, and also we have the training thread. And this is the simulation of this environment. On the left, we are using traditional algorithms to teach the robots to go and act. And these four robots, they are controlled by self-explored actors. And the benefit of using these multiple threads is that we can maximize the utilization of our PCs, so we can run multiple threads at the same time. And this is the results. So for the red lines, it is the using single workers, and the green line is using 6 workers. So we run 6 robots at the same time using nonlinear guidance law and simple collision avoidance algorithm. And for the blue lines, they are using 4 workers. And then we can find that so using single robots, we need around 6 hours to for the reward to achieve number 6. But using 6 robots or using 4 robots, we can achieve using less than 1 hour. So recall that using hummus data, we need 2 hours and 15 minutes to get the robots to learn to avoid collision. So using hummus data is 2 hours and 15 minutes, but using one robot even needs between 4 hours and 6 hours. But using multiple robots, we can achieve using around 40 minutes. But there's still something else I needed to do, because for the green line, using the traditional algorithms, we can see that it increases faster than the 4 workers without traditional algorithms. But for the following on stages, we can see that using these 4 workers, it achieves higher reward than even using 6 workers. That's because although we use multiple threads, our data efficiency gets diminished, because we have so many data using for the left 2 threads. Although it generates good data in the early stage, however, in the later stage, their data are not good enough, because they only have 1 obstacle, or it has no obstacles. So it's like a human. So when we are learning, so later on we want to learn some complex tasks. In the beginning, it's okay for us to learn from some simple tasks, so we can learn faster. But in the following period, we need to abandon this simple data. That's why using 4 workers, so it's even better than the 6 workers. So after a few hours, and that's also what ongoing work that I need to increase my I need to improve my my sampling strategy to make it to learn from this nonlinear guidance laws in the early stage, and then later on I need to abandon this data. So yeah, that's still one ongoing task. And so there are different ways. So there are 2 ways of playing asynchronous parallel learning. So one is like this, to share the experience data of multiple robots using multiple training threads. Multiple threads. And another way is what Joaquin's one PhD is doing to make these robots to share their trained gradients directly without sharing the experience data. And this is how we integrated them into the multiple robots to learn how to grasp one object together. So yeah, that's a different application. So we can implement these algorithms to mobile robots and also manipulators. Okay, that's all. Thanks.
Thank you very much, Hanlin. Any question for Hanlin? Maybe we can start the discussion between the different methods that we have seen. So in the first part, we have seen how to apply inverse kinematic with neural network. In the second one is also applying neural network. So maybe I wonder if the author have any feeling about the guarantees and the safeties that we can provide to this algorithm in terms of working in nuclear industries where safety is critical. No? Do you have any opinion about how to use neural network in this type of environment? Ozan, do you want to?
Yes, maybe this will not be directly a comparison between two algorithms, but I think they both share something, right? I'm really sorry.
Hanlin, do you have any? Because I have seen that, for example, some authors are, when you are learning or when you are using this kind of a scenario, they are imposing a safety in the learning. So if you are in the corridor, you allow your robot only to go 1 meter away from the wall. Have you seen this kind of work, or do you think this kind of work can be a solution for safety critical applications?
So for deep reinforcement learning, we can give it a very negative reward if it's closer, like to be less than 1 meter with the wall. Yeah.
Okay.
And for that deep reinforcement learning, its benefits is that it doesn't need to know the whole map's information. And because in the factory or in the industrial environment, it's very likely that our environment will change. We might have some moving obstacles, and also this obstacles information is not on the original map. So that's why we need mapless algorithms that only needs its local sensed data instead of the whole maps data.
Okay, thank you.
Can I ask a question to Hanlin? So in our approach, we kind of have an abstraction, and we can consider an object, the glow box, balls, or the other robot as objects, and we can embed them into our inverse kinematic solution and avoid. I think this is a bit crucial, because considering that in our mock-up system and in real life glow boxes, if you're using two robots through glow ports, they're quite close to each other, and collision between two robots is in a way inevitable if you're not careful. So I believe our approach is offering us an advantage here. How easy is it in Hanlin's DDPG algorithm to avoid collisions between two robot arms together with other things?
I think the challenging part is not the DDPG, but the one generalized method to model the environment. Because I'm helping Yinmo to implement his collision avoidance relaxed IK, and I found that his method using, so if we want to use a collision-free relaxed IK, we need to model the environment's obstacles. First is to sense them. So we need to detect this obstacle, and then we need to generalize the state of this obstacle. And what Yinmo is using is called a virtual marker of the RVs. So he just model all the obstacles as the virtual marker, and that information can be used as the input of his collision-free relaxed IK. Otherwise, because our obstacles, if we use point cloud for different obstacles, we have different sets of point cloud. We couldn't generalize them and model them. So that's the challenging part, I think.
Okay, thank you.
With respect to teleoperation versus autonomy, I mean, in which once we are putting a teleoperator there, and then we have in addition a collision avoidance algorithm, then the robot will not be following exactly what the teleoperator is trying to do, just because the other algorithm is telling you are going to collide with something. Maybe this is also a topic that deserve attention, I think. I don't know, what is your opinion about this kind of shared control, how the operator is going to feel when the robot doesn't move in the direction that the operator believes that it should move, just in order to avoid the collision with an obstacle. Maybe not with the end effector, but maybe the elbow is colliding with the wall, and the operator doesn't realize of this? And do you have any opinion about these kind of problems between teleoperation and shared autonomy?
I can comment on that if
Please.
there's no one. Okay, I think this is the sole reason why we should have collision avoidance in our inverse kinematic solutions. Both Pragna and I are interested in teleoperated solutions for globe boxes, and we are not doing any kind of autonomy. The teleoperation system we are building can be called unilateral. So the operator is sending end effector position or pose reference to the robot. So what robot should do is follow the given trajectories coming from the operator side. But how do you guarantee that the robot body, especially elbow, is not colliding with anything else? So one solution might be giving more control freedom to the operator by allowing operators to directly change the joint position values. But I don't think this is an efficient way of doing telemanipulation. It will definitely slow down the operations, and probably it's still not easy to grasp what's happening because robot is a much higher dimensional kinematics than what we are used to. So the inverse kinematics solution or any other mechanism should handle this. And this is why I call sometimes our work as an assistive teleoperation. It's not assisting the operator at the controller level, so we're not doing any kind of shared control when we use our multi-criteria IK approach, but we are reducing the task load by handling the collisions and giving operators more time to think about how to execute their task or plan their steps ahead. And as I said, this should be a mechanism in each Globox applications.
Any other comment from the panel, Hanlin or Pragna? Pragna, do you have any further comment to Ozan remarks?
Yes, actually,
Oops. You mute.
Hello. So Ozan actually replied everything. So I agree with him. And also, while we do the teleoperation, it's very important to know the collision while the robot is moving. Rather, before, if we have to calculate everything ahead, it's not possible in reality, because the glove boxes could be not be always visible every time wholly. So that's why we need the collision avoidance during the movement of the robot. That is the thing.
Okay, thank you. Bayo, do you want to add anything? Was a question?
Yes, so I have a question that I posted in the comments. It's just this, I'm just interested in the security consideration in the algorithms. What security considerations have been given for adversary actions, for instance, aimed to confuse the robots into colliding with objects within the environment?
Does anyone?
I
For
can answer.
the deep reinforcement learning, we just give it a very big negative reward to make it to not to collide with obstacles or some other constraints. So for some actions we don't like, we just give it a negative reward.
Ozan, do you have any additional information?
Well, this is something we didn't really consider in our application. So if you force the robot to a collision, then probably in our approach, we need a secondary level of security, which maybe stops the robot from moving. In our case, the robot will try to avoid, but if it fails, I think there will be collisions.
Do you have any further remark, Bayo, or is that clear?
But definitely this is a good aspect which Bio has put forward. And as Ozan said, we need an additional layer to control that, and we will further consider it. It's a good point. Thank you.
Yeah, so the Warwick University is working on the resilient machine learning project. Yeah, so these are part of the things that we are considering and we're working on. My name is actually Adibayo Bamitale. Yeah. So
actually, I would like to talk more about this. I mean, is it okay if I send you an email?
CC me also, Ozan.
Yeah, I mean,
yes.
at some point we need to consider with our algorithm, not if someone is hacking our algorithm or further security that we are going to add on the top of this kind of machine learning and sharing data and this kind of so for example in Hanlin, what happens if someone starts to give you wrong information about the sensors or something like that, then the robot will learn wrong things. Okay, guys, it's already 10:30, so thank you very much for the attention. I hope that you have enjoyed the presentation, this presentation. Thank you very much to Pragna, Ozan, and Hanlin for the presentation, and looking forward to see further development in this area. Okay.
Thank you very much for sharing.
Thank you, everyone.